Okay, I think we're good. I'm just gonna. Okay, so first problem. Prove that for a simple graph G in which all the n nodes have a degree of at least 2, there are at least n edges. So first of all, do we know what a simple graph is? Can someone tell me what a simple graph is? So, for example, is this a simple graph? So that is a simple graph. A simple graph is a graph with no loops and no multiple edges. So you cannot have edges that go like this. That is not a simple graph. A simple graph can only have one edge going from one node to another node. And there's no loop. There cannot be things like this. That's not a simple graph either. Okay, so how do you think we should approach this problem? Any ideas?
Draw a graph where every node has a degree of at least 2.
Sure, you can do that. Yeah, it's a you can do that and see if intuitively it makes sense. But there is this theorem. I think this is the chapter. This is kind of like the topic that you do need the theorems, and you need to know how to use them. So this is where your index card should help you on the exam. Try to write down the theorems and note what they mean and write down the definitions. So there's a theorem on page 13, like theorem 3, it says, so here's a kind of like a hint. So theorem 3, this is on page 513. It says, in any graph, the sum of the degrees of the vertices is equal to twice the number of edges. So what does that mean? So let's say if we have, let G be a simple graph, with n nodes. Then this is what it says, and m edges. Then we have I is equal to 1 to n. The sum of the degree, so degree of vi together would equal to 2m. Does this make sense? So the sum of the degree meaning what? So let's say go back to this simple graph right here. It's just a triangle like this. What is the degree of A?
2.
2.
Yes, exactly. Degree of A is 2, and then B, and then C as well. So actually, this graph satisfies the condition that it has, every node has a degree of at least 2, right? Because every node has a degree of 2. So you can see that there are 3 edges, and the sum of the degree is 6. So that's exactly what this theorem is saying. So how do we use this now?
Well, if each edge has a degree of at least 2, then the edges must be at least n.
Yes, you're right. So how do you get there?
Good question.
Okay, so the sum of degree, okay. So you're basically there. So let's go back to this right here. We have is equal to 2m, right? So this is from the theorem. So we know that is true. So now what else do we know? So we know that each node, there are n nodes, and each node has degree at least 2, right? So that means this right here, so this means the sum of the degrees of all the vertices, right? That means it's at least 2n, right? There are n nodes, each of them has at least 2. Okay, so let's put these two together. The sum of the degrees of the nodes is equal to 2m, m being the number of edges, right? And is greater than or equal to 2n, n is number of nodes. So 2m is greater than or equal to 2n. That means m is greater than or equal to n. So there are at least n edges. You can say, therefore, there are at least n edges. Does it make sense? Any questions? Okay, I hope you kind of know how we got here. So, should we move on? No? Any questions? Okay, fine. Next one. This one is, I think, easy. For the following set A and relation R on A, give the graph and adjacency matrix for the relation. So what do we do first? Let's draw the graph first. So what do I do? I'm going to start with 4 nodes. Let's say 1, 2, 3, 4. Okay. And then I'm just going to draw them like this. You don't have to. This is going to look really ugly, but that's fine. You can draw dots as well. But let's say 1, 2, 3, 4. So 1, 1, what does the edge look like?
Just goes to itself.
Goes to itself. 2, 3. We have 2 to 3.
Goes from 2 to 3.
Yep, exactly. Okay, 3 to 2. Goes backwards. 4 to 1, like this, and then 4 to 4 with itself. So this doesn't matter how you arrange the like the nodes. Like you can order them any other way as long as your edges are right. So your 1 could be on the left, your 4 could be at the bottom row, whatever. It doesn't matter. Okay, so what about the adjacency matrix? So first of all, what is the dimension of the adjacency matrix?
4 by 4.
Okay, 4 by 4. So we have 1, 2, 3, 4, 1, 2, 3, 4. What do I do now?
There's an edge between like the 2 nodes, then you put a 1, and if not, a 0.
Okay, great. So 1, 1. So always remember that the first, so like this is a row number, this is column number. So 1, 1 goes like this. Okay, so then we have a 1 here, and then 2, 3, like this. So we have a 1 here, and then 3, 2, 1 here, 4, 1, and 4, 4. And the rest of them are zeros. You can just fill them in. So normally, you can kind of imagine, right? This graph right here, this is definitely not a simple graph, right? This is not a simple graph and it's directed. So this is a directed graph. And because it's a directed graph, we have this asymmetrical matrix, adjacency matrix. Like, you know, it's not symmetrical across the diagonal. But if you have a simple graph or like an undirected graph, a simple graph, let's say, So you only have one edge, like something that looks somewhat like this or whatever. You can imagine that every time, say 1, 2, 3, 4, 5. Every time there's an edge from 1 to 2, there's the same edge also appears with 2 to 1. So you end up with a symmetric matrix. Any questions about this? Okay, let's keep going. Prove the following statement. Let UV be vertices in a graph G such that there exists a walk from U to V in G, then there exists a path from U to V in G. So first of all, what is a walk?
Just like a path of edges and vertices to get from one to the other.
Mm-hmm. And then does it have any restrictions or? Not really, right? So like walk is probably the most general. So basically it's like a, what is the definition? A list of alternating vertices and edges. Yeah, but then the restriction is that the edges has to be between each vertices. You cannot have an edge that's like kind of out of the way, like somewhere random. And then what about a path? What's a path?
No repeated vertices.
Yes. Okay. A walk with no repeated vertices. So do you guys have any idea how to do this? Take some creativity. So like, do you kind of see why intuitively this makes sense?
Yeah, I mean, if there's a path from U to V, there's a path from V to U. You just walk backwards.
No, this isn't walking backwards. This is saying there's a walk from U to V. There's also a path from U to V.
Oh, yeah, I see.
So what is the difference between, go ahead. I think someone muted themselves.
I guess if there's a walk, that means there could be repeats. So you just like kind of take out the repeats and like build the path out of that.
Yeah, exactly. That's exactly how the proof works too. So you can imagine there's like, there can be cycles, there can be like random stuff going back and forth, because a walk can be anything, right? You can literally go from one to the other and just go back and forth and back and forth and back and forth and then keep going afterwards. So then what you need to do is just take out this chunk that's the repetition. So how do we how do we write this then? So like you can, so I think that the important part is to kind of see that the shortest possible walk. A walk is the length of a walk is how many edges that's in between, right? The number of edges that's in the walk. So you can kind of see that you have to see that the shortest possible walk would be that path. And there could be multiple, you know, like we're not saying that the path is unique, right, from U to V. There could be multiple that's the same length, and there's it's the shortest length. So what we're gonna do is to actually say let V0, so V's are vertices and edges are E's. So V0, E1, V1. Let's write a few more. And then Vn minus 1, En, and Vn. So let this be the, what happened? Give me a second. Be a walk from U is equal to V0 and V is equal to Vn. So 2. Okay, so let this be a walk from U to V, right? With the shortest possible length. So we claim this walk is the path. We're looking for. So that is to say that, let's say this walk is, let's say this walk is W, okay? So that is W has no repeated vertices. So that's what we claim. So we're claiming that the shortest possible walk is the path that we're looking for. So now how do we prove the claim? When we prove the claim, we prove this problem, right? We're done with the problem. So how do we prove the claim? This is exactly the same thing as the logic that we talked about before, is to remove the repeated part. Can you guys still hear me? My Zoom is like really stuck for some reason.
Yeah, we can hear you.
Okay, I'm just gonna, can you see my slide? Oh, I think it's just, okay, it's just super slow. Okay, that's good. Okay, so how do we prove this claim? How do we prove the claim that we just talked about? Any proof techniques that you can think of that we can use here? Clearly, it's not gonna be induction. Anything else? So we're going to use proof by contradiction. So let's say we prove by contradiction. So if we want to prove by contradiction, what do we assume to be true? So remember the claim back here, W has no repeated edges. So what do we assume to be true if we want to use contradiction?
Then in order for a walk to exist between U and B, it has repeated edges.
Exactly. Repeated vertices, right? It has repeated vertices. Okay, so suppose the walk W contains repeated vertices, and let's call them VI and VJ. So they're the same. So let's do VI is equal to VJ for some I is less than J. So just to make sure that they're not, I and J are not the same thing. We're not talking about the same vertex. We're talking about two different two vertices in different positions in the walk, but they're the same vertex. So let's say that this is the repeated vertices that we have. So what happens now? What do we do now? Like, this is the repeated stuff. There are edges in between, right? There are edges in between. So like you can imagine this walk looks somewhat like V0, E1, V1, and then somewhere in between there's like VI, right? EI plus 1, and then like VJ. And then it keeps going until VN. right? So what do we do here? We know that these two are the same vertex. What does it tell us about this path right here, like this walk right here in the middle? Is it necessary? Do we need? No, right? Do we need this to go from V0 to Vn? We don't really, right? So we can take this out. So what we're going to do is that we're going to say that then we remove the walk between Vi and Vj. So the only thing we need to do is to keep Vi. So we have that vertex, keeping Vi. And create a shorter walk from V0, which is U, to Vn, which is V. So there's a contradiction there. We claim that W is the shortest possible one, and we just found a shorter path. We just found a shorter walk. So there's the contradiction. So this is a contradiction. Since we assumed W to be the shortest walk from U to V. Therefore, W is the path that we're looking for. It has no repeated vertices. Does it make sense? Any questions? Okay. Then shall we move on? Okay. Prove the following statement. Let G be a bipartite graph. Prove that every cycle in G has even length. So what is a bipartite graph? You guys should really write the definitions down, like for the final. I think this chapter is the one that has the most amount of like kind of new definitions that you kind of haven't thought too much about before. So write them down, write the theorems down, and know how to use them in practice. So what is a bipartite graph? Let's see. So where is it on the book actually? Oh, it's actually on the book. Okay, the definition of a bipartite graph. Bipartite graph. This is on page 536. Okay, so it says, a graph is called bipartite if its set of nodes can be partitioned into two disjoint sets, S1 and S2, so that every edge in the graph has one endpoint in S1 and one endpoint in S2. So like simple example, something like this, right? This is your S1 sets of vertices, and this is your S2 sets of vertices. And then you can only have edges that go something like this. This is not a connected graph right here. I don't know if you can tell, but like you can see that this walk right here from like, let's say 1, 2, 3, that's not connected to the rest of the graph. And 1, 2, 3, okay, like 4, 5, 6, 7. So this 4 to 5, 5, so 4 to 5, 5 to 6, 6 to 7, 7 back to 4. And that is a cycle. The cycle cannot have repeated vertices except for the one that's starting and ending. So 4 is the only repeated vertex in this closed walk. So can you think of why every cycle in G, so let's say this is our G, can you think of why every cycle in G has even length?
If it starts from the first set, it has to go to the second and back, or like
Right.
vice versa, I guess.
Right. Basically, that's kind of what it is, right? You always have to go between the two. You cannot move within the set itself. So like you always have to go back and forth twice, kind of. So it's always going to be even. So how do we prove this? I think this one's a little tricky, but it's not super difficult. I think it would make sense when we do this. So let's start with, suppose G is bipartite. Then by definition, vertices in G form partition V1 and V2. Okay, so let's start with the cycle. Let V0, V1, Vn minus 1, and go back to V0. The cycle goes back to its origin, right? Be a cycle of length n. So where do we go from here? Think about where the vertices belong. So we now have a partition here, right? We have V1 and V2, like these two sets. And then we have the cycle right here. Where do you think the vertices belong? Let's say that V1, let's say that V0 here, let's just say like V0 here belongs to V2. Then where does the V1 belong? Actually, let's change them to S1 and S2. This is like too hard to talk about the differences. So this is S1 and S2. Let's say that V0 belongs to S2. Where is V1? Can V1 be in an S2 too, as well?
It has to be in a S1.
It has to be an S1, right? So it has to be an S1. So what does that mean about Vn minus 1? Because remember, this is V0 goes back to the origin, right? So this is still S2. So where is Vn minus 1?
Also an S1.
S1. Yeah, so can you see a pattern here? We have even indices. So you can imagine, okay, so you can imagine that V0, like we said, suppose that V0 is in S2, then V1 is in S1, right? And we keep going, V2 is in S2, right? V3 is in S1 again. And we go to Vn minus 1, that is in S1, right? So you see that the even vertices belong to the even set, like S2, right? And then the odd vertices, so V3, V5, V7 belong to S1, the odd set. So what does that tell you about n minus 1? Is it an even or an odd number?
Odd.
Yes, exactly. It has to be odd, right? Because only the odd indices can be in S1, right? So n minus 1 has to be odd. That means n has to be even. This is odd. That means n has to be even. And n is the length of the cycle. And we just proved the statement. Prove that the cycle in G has even length. We just proved that n is even. And n is the length of the cycle, as we assumed here. Be the cycle of length n, and n is even.
What if we were to do it such that we started with V0 as an element of S1 and not
Sure.
S2?
Yeah, sure, we can do that, right? So like if V0 belongs to S1, then where is V1? Let's say if this is an S1, where is V1? Remember, the edges have to go back and forth. You cannot have an edge that goes from S1 to S1, right? You have to go from S1 to S2 and back to S1 and back to S2, right? So then if V0 is an S1, where is V1?
It would be an S2.
Yeah, exactly. It's be in S2, right? So then V2 is gonna be back in S1, right? So okay, so like it's the same thing, right? So if we have V0, V1, V2, and then Vn minus 1, and then V0 again. So if this is we said S1, then this has to be in S2, and V2 has to be in S1 again, right? And V3, let's say V3 here, has to be in S2. So this is V0 goes back to the origin. That's still in S1, right? So what about Vn minus 1 then?
It'd be an S2.
Yes, exactly. This would be an S2. So we see that all the even indices are in S1, right? Like the V0, the V0, V2 are in S1, and odd indices are in S2, right? So that means n minus 1 is even or odd. Vn minus 1 is in S2, right? So that means n minus 1 is even or odd.
It would mean that n minus 1 is odd.
Yeah, n minus 1 is odd. That means n is even. And the cycle is of length n. So cycle is of length n. And n is even. So QE, draw a little box. We're done. Does it make sense? So it doesn't matter which one you start with. You just have to know that it alternates. It cannot go from the same set to the same to the set itself, right? You cannot have you cannot have edges that go inside of S1. It has to go across to S2 and back to S1 and to S2. Do you guys want me to like write the rest of the proof? Because like basically up to here, it's still a formal proof. Basically up here. And after that, we've just been talking about it. Do you guys want me to write it out for you?
Sure.
Okay, anyone else? Sure, we can write it. It's not very difficult. We're just trying to explain this process. I think this is more of the type of proofs, if you actually go on to do more proofs, this is more like the proofs that you will be doing in the future. It's more like writing essays instead of doing math. Yeah. So, like, let's just keep going from here. So we have, let this be a cycle of length n, right? So suppose V0 is in S2. Then V1 has to be in S1. V2 is in S2. V3 is in S1, and so on. Since V0 is in S2, then Vn minus 1 has to be in S1. Okay, in other words, odd, let's say vertices, okay, so vertices with odd indices are in S1. N minus 1 is odd, then n is even. So I'm just gonna go here, n is even. Okay, and then you can just like write a conclusion. Therefore, the cycle of length n is always even. And QED. Any questions? Okay, so now we're done with the graph problems. We can go back and talk about questions on the quiz. So we included, actually, let me see, 2 and 3 from the quiz. Do you guys have a preference on which one we go over first? Because I don't know how much time we have left. I don't know if we have enough time to go over both, but like, any preference? You can type or unmute yourself.
You said question 2. What was the other one?
and 3. So 2 is the 777,555 thing, and then the 3 is the 30 children, and lining them up one.
Let's do 2 first.
Okay. Any other strong opinions? No. Okay. So let's do 2. So how many different ways are there to form 7-digit strings having no zeros? So basically we cannot use 0. We only have 9 digits here, where we only distinguish between the number of appearances of each digit. For example, 7777, 555. They're the same, so that means the order does not matter, right? So that the rest of it is just to explain what happened. So basically here, first of all, identify. We already said order does not matter, right? What about repetition? Do you have repetition here?
Yes.
Yes. Okay. Repetition. Yes. So what kind of problem is this?
Be a bag.
Yes, a bag problem. Okay, so how many different ways are there to form 7 digits with basically 9 different digits, right? So form a 7-digit string with 9 different digits. So what do we do? This is basically something that looks like, we can use x or n, whichever. So x1 plus x2 plus x9 is equal to 7, right? So each of these are the digits, and then x1 is the number of times that one happens to be in the string. So how many different ways? What do we do now?
Would be C of 15, comma 7.
C of, yes, 15. So how do you get 15?
9 plus 7 minus 1.
Yep, 9 plus 7 minus 1, and choose 7, right? Because that's the length of the string. So that is 15 choose 7 or 15 choose 8. They're the same. 15 choose 7. Or 15 choose 8. Okay, so, any questions about this? This should be the simple part. So what about B? Answer the same problem above, but with the constraint that each instance has no more than 2 7s.
Could you use complements?
Okay, how do you use complement? What is the complement?
A complement would be strings with 3 or more 7s.
Right, okay, strings with 3 or more 7. So how do you find the number of possible combinations?
Could you do the same thing you did before, like x1 plus x2 up to x9, but instead of setting it equal to 7, set it equal to 4?
Okay, x1 plus x2. But then, right, okay, so I think, yes, this is 4, right? Why 4?
Because you have to have at least 3 7s in there.
Right, so the string is length 7, right? But we already have 3 spaces taken, so we only have 4 left. So you do the same thing. So that would be what?
That would be C of 12, comma 4.
Yep, C of 12, comma. Wait, 1 second. Yes, actually, that's right. So that is also the same thing as C of 12, comma 8. Like, it doesn't matter. Same thing. So how do you get 12 again?
From 9 plus 4 minus 1.
Yep, 9 plus 4 minus 1. So that's 12, 4. Okay, so what is the final answer then?
So then I did C of 15 comma 7 minus C of 12 comma 4.
Yep. Okay, so alternatively, you could also do, string with 0, 7, string with 1, 7, string with 2, 7. You add them up together. This is just an easier way of doing this. Does it make sense? Any questions? Okay. So what about 30 children? We have 30 children. Assume no 2 children. So we have 15 fourth graders and 15 fifth graders. And assume that no 2 of the children have the same name. What is the probability that the children appear in line in alphabetical order?
Could you just do 1 over 30 factorial?
Why is that?
Well, because it'd be permutation of 30 comma 30 for the total orders of all 30 children. And then there's only one way to put them in alphabetical, right?
Yeah, exactly. There's only one way of putting them in alphabetical order. And then, so basically this is n of event, right? So the number of events, and then bottom here is the size of the sample size, which is 30 factorial, or permutation 30, comma 30. You're arranging 30 kids, and there are 30 spots for each one of them. Okay, so what about the second one? What is the probability that all the fifth graders precede the fourth graders? So what does that look like? Basically, you have these 2 separate arrays or lists, whatever, lines. So these are the fifth graders, right? And these are the fourth graders. And the fifth graders, there are 15 of them, right? 15 of them. And there are 15 fourth graders as well. They can permute within themselves. So in here, they can permute within themselves, and they can permute within themselves, but they cannot move outside of that 15, right? So what does that mean? We still have the same sample space, which is, so like down here, it's still permutation 30, comma 30. Because these are all included in all the possible combinations. So what about on top? What do we do now? How many different ways can we line them up?
P of 15, 15 for both, right?
Yes, exactly. Because we're arranging 15 of them, and they can permute however they want. And then we have the same thing for both of them. And then you can imagine one combination in the fifth graders can pair up with all the different combinations in the fourth graders. So that's why we multiply them. So this is basically 15 factorial times 15 factorial over 30 factorial. Okay, so the last one, what is the probability that they alternate by grade in line? So let's say we start with a fourth grader, then the next one has to be a fifth grader, and the next one has to be a fourth grader, right? So, and there are 30 of them. So we can also have the other situation where the fifth grader starts, and then we have a fourth grader, and we have a fifth grader, right? So how do we compute the probability of let's say the first one? It's still the same thing, right? We have 15 spots for fourth grader. We have 15 spots for fourth grader. They can permute within themselves. The fourth graders are here, and then the fifth graders are here, right? So we always have 15 spots for fourth graders. We have 15 spots for fifth graders as well. They can permute within themselves. They just cannot permute into the other set. So a fourth grader and a fifth grader cannot switch spaces, but a fourth grader and a fourth grader can, right? So that means it's still the same thing, right? Permutation 15, 15 for fourth graders, permutation 15, 15 for fifth graders, right? Over 30, 30. So that is just one case. So we have two cases here. So 1, 2, right? The first case is that fourth grader starts. The second case is that fifth grader starts. So that's why we're going to multiply by 2. So this is also 15 factorial times 2 over 30 factorial. We're out of time, but if you have questions, please ask them. Please ask them now or go to office hours. I hope this is helpful. If not, have a good one.